Okay, it's 6 o'clock sharp, and we welcome you to today's webinar regarding need for speed, protein dynamics in stop flow applications with dual-com spectroscopy. I'm very happy to present you today Cédric Georges. Cédric graduated in analytical chemistry from 2 universities in chemical engineering. He graduated from Swansea University in '99 and in Montpellier from France in '98. Cédric is now product manager and responsible for all rapid kinetics and spectroscopy instrumentations at BioLogic. Cédric led the development of the last generation of stop flow mixers, the SFM 4000, such as the stop flow dual-com spectroscopy coupling described today. I'm very happy and honored to have you here today, Cédric.
Hello, everybody, and thank you for attending this webinar. And thank you, Florian, for my presentation. So I would also like to introduce you my co-speaker today, Florian Eigenmann, also PhD in chemical engineering from ETH Zurich, and he joined IRSweep in 2018 as business development manager. Before working for IRSweep, he has some sales responsibility at Bruker and Mettler Toledo in near-infrared instrumentation. And at IRSweep, he was instrumental in releasing the high spectral resolution version of a dual-com spectrometer and in developing some rapid kinetics application like stop flow. He did the preliminary test in the company, and it is how we actually met and how we decided to do this webinar together. So Florian, go ahead.
Thanks, Cédric. I will just briefly give you an overview about the benefits and some selected applications of dual-com spectroscopy. We'll specifically discuss the speed advantage of dual-com spectroscopy over other spectroscopy techniques. And then hand over to Cédric in roughly 15 minutes. So there are several benefits when talking about QCL frequency comms. One is the speed advantage, which will be the body of this talk, with high time resolutions in the order of micro or even also micro milliseconds. Another one is the brightness. The dual-com spectrometer is using a strong laser source, which are orders of magnitude stronger than thermal light sources such as the globular source. Another one is actually that you can measure complex mixtures. So those complex mixtures can be identified or monitored with, because we are recording not just one single line, so there are several laser lines available. And last but not least, there is a high resolution version, as Cédric mentioned just before, of the IRSF1, which allows to record 0.001 wave numbers, so 1 milli wave number resolution or better in a few minutes. As I mentioned before, we focus today on the speed advantage of dual-com spectroscopy, and those are some data, and here you can see some data of an early publication with Tillmann-Kottke with the bacterial rhodopsin cycle, when the technology has been validated with STEPScan FTIR. Diving a little bit more into the technology, I explained the main principle in a nutshell now. So there's actually, you have 2 frequency comms. Those beams are mixed on a beam splitter and detected on a high bandwidth MCD detector. Each pair of those optical modes produces a radio frequency beat node, and the radio frequency spectrum can be measured with conventional electronics and represents the optical spectrum. So why is that fast compared to other spectroscopy techniques? For example, FTIR spectroscopy. So you have no moving parts, and you have such really strong lasers, which gives this excellent signal to noise. So it's not just that you can measure really fast and acquire very fast spectrum, you get also a really good SNR. For example, in 1 microsecond, we get already an SNR of roughly 100. And that allows single shot analysis and really microsecond reaction monitoring. With an open beam measurement, we present here a heterodyne signal, which were obtained with a 1650 laser. The 1650 laser is a very popular one, which is used to determine, for example, secondary structure in bio biodynamic protein dynamics, and was also used in the following studies for those stop flow measurements we achieved together here in Switzerland. Furthermore, you can actually detect the water vapor in the range. So the dips here, as you can see, the dips of a hydron water vapor represents actually then absorption. So you can do absorption spectroscopy, and you get actually the information of those water vapor band with very thin lines. Since the spectrometer has a large sample compartment, probably it's one of the biggest sample compartments on the market, you can almost use all the accessories which are currently available. And I'm very happy actually to see in the audience also people from Herrick and Speccock, some product managers, and all those accessories. For example, you can see here the praying mantis or Golden Gate ATR fits perfectly in the sample compartment and can be used with the iris SFM. So the big picture on the right, and also to mention that, shows also that we were coupling already an FTIR ATR probe, as an ATR probe of 10 meters. It's a fiber optics ATR probe, and due to the strong laser source, we were able to detect similar sensitivity than with a standard 2-meter or 4-meter lab probe. One of the key cornerstones of the iris SFM is the change of a laser module, which can be done in roughly 30 seconds. So you can see here, we can see here Pierre, one of our senior engineer, who disconnects the chiller. So he disconnects actually the water supply, which makes the stability, laser stability or temperature stability of plus minus 0.05 Kelvin, which is necessary to obtain those excellent results we will see later. So after connecting, for example, another laser module, you're good to go after probably another stabilization of 20-30 minutes, but then you can rock and roll and perform other applications at other wavelengths ranges. The laser availability list is what we discuss the most and that we are very proud of. We fill the gaps as we speak. I want to highlight two main lasers. One is definitely the 6050 laser, which we will see later. And we call it sometimes also just the amide-1 laser. It's very popular, as I mentioned before, for protein dynamics. And then the other one will be at 1240. That's a laser module, which is already very broad. It's indicated here with 80. We have first results in R&D that we have even chips that we can go over 100 wave numbers. Sorry, I think that's a little bit enough about technology. I want just to highlight a little bit applications, and we'll show two major applications. I had just yesterday a call with the company Dilo. They are really having a nice application which shows the strength of this dual-com spectrometer. So you can see here that the reaction or this glue is irradiated with UV light, and the reaction goes over a few seconds. So this is the live view of the live spectroscopy view around 60-50 of this reaction with a few seconds. You see the time scale is very fast. And since today, conventionally, this was done by FTIR spectroscopy, sometimes rapid scan FTIR spectroscopy, but due to the fast reactions, people were monitoring just a scan at the beginning and at the end of the reaction, just to see the quality of the kinetics. So the kinetics itself was difficult to monitor, but to see actually if the quality is good for the kinetics. There's a limitation there. I will come later to this topic. So the data which we observed now, and we are very proud that we always have a little bit to update the slides, and actually also because we did a lot of the technical updates last year, we are able now to achieve 1000 spectra per second. So you see actually this reaction here, just like a band which goes down, and at 1655, and another one at 1630, which goes up. And like this, we were able to monitor in 5-6 seconds, very impressive signal to noise in this area. Going once a little bit back to another technical point, which terminology we use later on. There are basically two modes, which is important where we talk about long-term acquisition mode, and we mean here seconds. So even if it's long-term, but that's more probably continuous, we call that long-term acquisition mode, and this can be used now and performed with 1,000 spectra per second at 0.3 resolution. Then we have the time-resolved mode. The previous length was 131 milliseconds, and before it was even less, but now we extended that to 268 milliseconds. And this is not only much faster than before, and we reported actually a year ago like 25 spectra per second, so we can also measure consecutively much longer with this 4 microseconds time resolution, which is outstanding. So we get 4 times longer continuous data acquisition, namely 67 milliseconds before, then it was now 131 milliseconds, and now even 268 milliseconds. There's a lot of information on that plot, and I don't want to rush through that plot. So you can see actually on the y-axis the spectral resolution, and on the x-axis the time resolution. And I put once all the FDIR spectrometer there because there's always a dependency between spectral resolution and time resolution. And some applications overcome that with so to optimize actually the time resolution, you lower spectral resolution. So there's always a trade-off what kind of resolution you need. So if you want to measure as fast as possible, then you lower a little bit the resolution in FDIR spectroscopy. Those are all the commercial available spectrometers. And you can see 2 spectrometers, or 1 spectrometer actually with 2 different parameters in the Joachim Heberle lab in Germany. He did a homemade scanning interferometer and achieved there 13, respectively 26 microseconds. So really good time resolutions with a wave number, or with a spectral resolution of roughly 5 to 9 wave numbers. The problem was just the SNR, the signal to noise, was not that good. So he's, and we are very proud actually, he's one of the first, or he's the first user of the IRSF1 where he really gets hold of, or he's really using this fast measurement possibility where we have this 1,000 spectra per second continuously, or as mentioned, the microsecond time resolution where you have 1 million spectra per second in 268 milliseconds. There are a lot of other applications. I will just highlight actually also that some experts in the field, some dual comp champions talked already a lot about those different applications last year. They are still recorded and you can have access on demand. One which I want to highlight is just recently in March, Carsten Kötting showed some results on cage compounds, which highlights actually the need for dual comp spectroscopy on non-repetitive protein reactions by applying those compounds which are which cannot be monitored with other technology, with other spectroscopy. Carsten highlights also, he makes a comparison with instruments which are already on the market, that with FDIR rapid scan, he can not only has a certain limit of 50 milliseconds time resolution, and that with a dual comp spectrometer with the IRSF1, you can go 3 orders of magnitude faster and really dive into a new time domain, which is in the order of microseconds. Now, I really want to dive in the stop flow applications, and specifically now, of course, with dual comp spectroscopy, which is, yeah, I just outlined it very briefly because Cédric is definitely the champion, and he can, as a product manager, knows much more about stop flow than I do. Nevertheless, the first measurements we did was like here in Switzerland in 2019 with my colleague Raphael Horvath. We measured just on a standard or manual setup with an ATR unit, and a stop flow device from Thermo. Such two reaction which was in the low digit second range. So we mixed those together. You see this in a zoom in, and this was a A to B, of A and B reactions to C, and at that time we were able to measure like roughly 50 spectra per second, which is roughly with 20 millisecond increments. It's actually what I really want to mention. We saw already some really nice things for syringe movements. You can see that here that the early time domain, the kinetics was dominated by syringe movements, but it was still possible to fit bioexponential decay, which was observed at later times. I think that's really nice. What was already possible just with the manual start of that and triggering manual, and that's actually a really nice part where I want to hand over now, and it's really time to look into professional stop flow setups. And I'm very happy, as I mentioned already, that Cédric is with us today, and he will walk you through the setup and the results he achieved during the lockdown last year in Switzerland. I think it was Cédric's only visit out of France, as far as I know. And I think, Cédric, please go ahead and walk us through the technology and the applications and the results. Right. Please go ahead.
Thank you. So I would like to do a brief introduction to stop flow for the people who are not specialists in such instrumentation. So what is the principle of stop flow? So a single mixing stop flow is a 2-syringe instrument. So each sample is loaded in a syringe. Then you push solution into a mixer at a constant flow rate. So the mixed solution flows through an observation cell. And at one point, you stop the flow instantaneously to measure the change of signal induced by the chemical reaction in the cell. So the performance of the stop flow instrument rely on the technology used to stop the flow and on the quality of the mixer used. So to stop the flow efficiently, so to avoid to have some elasticity in the system, we use a stop valve we call the R-stop, which is synchronized with the stop of a pushing mechanism. The mixer technology used is a ball mixer. So this ball mixer was designed to create some turbulence mixing in the widest range of flow conditions. It means you only need to have one solution arriving fast in the mixer, or you could work with large mixing ratio. You could have large change of viscosity, change of temperature, and the mixing will always be turbulent. So you could see from the small sketch that you have one solution entering the mixer from the bottom of the mixer, and the second solution is injected in a throat all around and enter the mixer through small holes, which will create a kind of vortex inside the mixer, and then the final solutions go up. So a stop flow experiment will always be divided in 3 different phases. You have the pushing phase, which generates the mixing, then you have the stop of the flow, and then the observation. So what are the main points of the BioLogic technology? So I just showed a scheme before with 2 syringes, but you could also have 3 or 4 syringes. That means 2 or 3 mixers if you want to do multi-mixing experiment. We use an independent stepping motor drive. It means the user has a full control of the volume he delivers, a full control on the speed, and also on the mixing ratio. And thanks to this independent motor, the user could also do some automation. It means you could program a series of concentration, or you could change the aging time just by playing with the software. In terms of speed, so the shortest dead time you could do is 200 microseconds. But this minimum dead time may depend on the size of the observation cuvette you are using, and sometimes the limitation could be the speed of the detector. The independent motors also offer some modularity, as the system is not confined to stop flow application. You have the possibility also to use the same unit to do other closed technique like freeze quench, chemical quench. And one of the major points is that the stop flow was developed completely independently from optics. It means that the stop flow could be easily coupled to external detectors, and this would be our case today with the DCS coupling. So here I just refer to the mixer, but if you want to do a stop flow experiment, you need to mix and you need to detect. So at BioLogic, we have some in-house optical solution. For example, if you want to see change of absorbance, fluorescence, circular dichroism, anisotropy, conductivity, for example, if you have some change of ions concentrations, then we have some rapid detectors. But there are some techniques where we need to couple our instrument to external spectrometers. So in the past, we have already coupled the stop flow to neutron scattering, to X-ray, so it could be some beam lines or also benchtop X-ray, dynamic light scattering instrument, FTIR, and now dual-com spectroscopy. So you have two ways to couple the stop flow to an external system. The first one, if you have enough space around the beam, then it is possible to put directly the stop flow and the observation head in the beam. If not, we have a small accessory we call the umbilical connector. So this is the picture on the right. So it fits directly on the chassis of the stop flow, and you put the observation head on one end of the umbilical. So this umbilical cord adds some priming volume, but the volume you use per experiment and the dead time are exactly the same. So in that case, we just fit the observation head inside the sample compartment. And this is the technique we're going to use for the DCS coupling. So what do we need? So we have the stop flow, of course. Then we have this umbilical connector. So for the picture here, we have removed the temperature jacket of the accessory, because normally you could control the temperature of the reaction. So you have the full control from the syringe to the cell. So here on the left picture, so we see these green tubes, which are just the priming, some kind of HPLC tubing, bringing the solution from the stop flow chassis to the observation cell, which is on the back, and we see it in the sample compartment. So what else do we need? So we need the stop valve to stop the flow, and then to synchronize the two instruments, we need a 5-volt TTL trigger signal. So it is just a connection through some BNC, so it's very straightforward. Now we'll describe the cell we are using for such experiment. So we use some standard FTIR flow cell made of calcium fluoride, but some other materials may be used. The light path is selected using PTFE spacers. So in stop flow application, you could vary the light path from 100 micron to 500 micron. So it could be easily changed by the user. So on the scheme on the right, you see how the cell is built. So you have a holder for all the different places, and it is set by layers. So we put a gasket, that one window, the spacer for the light path, the second window, and when everything is fit together, then we put this part on the mixer holder. So this is the picture on the left side. So on the picture on the left side, I haven't put the umbilical, so we have a clearer view of how it is organized. So we see the two small holes in the middle, so it's where the two solutions will come from. The mixer is inside the gray part, which is made of PIC. So the mixer will be as close as possible to the observation cell, so the dead time is minimum. And then the tube at the exit is going to the waste, and is going to the hard stop and then to the waste. If you need to work with some organic solvents, it is also possible to equip the full instrument with some Cal-Res O-rings, so you have a full solvent compatibility. So it's also an option. It's not something we do in this experiment, but something we could do. In terms of software, so we use, to control the stop flow, we use our BioKinase software. So thanks to the stepping motors, we know precisely in the software the exact volume of solution we have in each syringe. Then to design the experiment. So on the right side, you have what a typical mixing sequence looks like. So there are 3 parameters we need to set. We need to set the mixing ratio, the total volume we want to push, the total flow rate. Then the software gives you an estimation of the dead time. And then you also have the possibility to add some pre-trigger. So you have a choice. You could trigger the detector at the time of a stop or few milliseconds before. Usually, it is convenient to do it few milliseconds before, so we are sure we are reaching stationary state. And in that case, with DCS coupling, we could use this pre-trigger to do a background measurement. Another interesting thing for the user is the color code we are using in the software. So here you see that all the parameter boxes are set in green. So it means we are in ideal conditions, so it's safe to run this experiment. When one of these boxes turns to orange, it's just a warning for the user that you are closing to a limitation. And for sure, when you go outside the specifications, it turns red. So the software will not run the shot. So you will not take the risk to lose precious sample or to break anything. The data acquisition itself will be made with the IR sweep software. So what experiment we have chosen to do coupling? So we selected the beta-lactoglobulin folding using trifluoroethanol, TFE, as described by Gervert and his co-workers in 2001. So the beta-lactoglobulin is mostly a beta sheet protein, and the beta sheet structure very rapidly folds to alpha helix via a very short lifetime intermediate when we mix with TFE. And because beta sheets and alpha helix have clear absorption bands in the mid-infrared, the change of secondary structure could be followed by DCS. So what was the mixing sequence used? So first, we loaded the protein in 10% TFE in one syringe. So here it was syringe 4. And in syringe 3, we put just TFE 60%. So we're going to do a 1-to-1 mixing ratio to create a TFE concentration jump from 10 to 35% to initiate the folding. So here we were using 200 microliter and the total flow rate was 3. So we have an estimated time at 5 milliseconds. And we use the pre-trigger to measure the absorbance background, as I said earlier. So what were the results? So on the left side, we see the infrared spectra obtained during the first 10 milliseconds of the reaction. So with a small offset, so it's easier to see. And on the right side, we have a timescale recording during 100 milliseconds at 3 different wavelengths for wave numbers. So what do we see? So the spectra measure in the first 10 milliseconds confirm the existence of an intermediates with bands at 1660 and 1634. So the fall we see at 1634 is related to the loss of the beta sheet structure, and the signal increase at 1660 is related to the creation of the alpha helix. Even a small intermediate at 1644 could be monitored without using any chemometrics such as PCA or other deconvolution techniques. The reaction was finished in about 100 milliseconds, and the signal to noise was very good comparing to some other coupling of stop flow with FTIR with the same reaction. So right now we only did a single mixing experiment. So we could have the possibility, because we have 3 or 4 syringes, to study some influence on the concentration jump of TFE. So for example, the first mixer could be used to adjust the concentration of TFE, and then we do the second mixing to follow the second reaction. So in the software, you could do some automation. So you tell the software, I want to go from this concentration of TFE to another one with a given step. And the software will calculate automatically the mixing ratio to apply between the syringe. And at each injection, you will trigger the TCS spectrometer. So you just need to synchronize the length of the data acquisition with the next injection. So this is all made with TTL signal. In case one of your reactants is unstable, you have the possibility to use the first mixer to generate this intermediate. So you mix two products, you define a waiting time or incubation time, and after this time, you mix this product in the second mixer with the third sample, and you follow the second reaction. So this could be fully automated in the software also. So what could we expect from such coupling? So we could expect a 5 milliseconds dead time. Sample consumption will be between 75 and 100 microliter per experiment. So this is when you use a 1-to-1 mixing ratio. So if you do asymmetric mixing, for example, if you do a 1-to-10 mixing ratio, you have a possibility to reduce the sample consumptions down to 20 or 25 microliter with one of the sample. The umbilical, 200 microliter, normally it's enough, but you could have longer ones in case you have some real space limitation around the spectrometer. So you could do multiple mixing. You could change the light path, 100 micron to 500 microns. So it takes about 5 minutes for a user to go from one light path to the other one. So it's very straightforward. You can collect infrared spectra with a 4 microsecond acquisition time, which is very fast compared to other experiments made in this region before. You could collect up to 1,000 spectra per second in continuous reactions and with a 0.3 centimeter resolution. And the background noise you could expect is about 1 millidegree of absorbance unit. I would also like to thank Jacob Hayden from IRSweep, who run the Stopped Flow experiment with Florian and me when I was in Staffa last winter to do this experiment. If you want to learn more about this coupling and about this experiment, there is a full application note available on the BioLogic website. The same notes with the same results is also available from our collaborator at IRSweep with different layouts, the company layout. So Florian, if you want to continue.
Thanks, Cédric. I just take quick the slide over, the slide deck. I think you just stopped here, and thanks a lot for this excellent contribution. I see already that some people actually use already the Q&A session tab and drop some questions there. I encourage everybody to do so as well. The first question which we got is actually, do you see heating of the sample due to the intensity of the IR beam in the stop flow case? Solvent absorption is usually 0.5 OD, a little bit larger than 0.5. What spacer thickness did you try out with the solvent water? Do you remember what kind of spacer we were using?
We use a 100 micron for this experiment. Yeah, this is the one we use, and well, you could use 100, 200, and 500 microns.
Yeah, I think that's one of the big advantage actually working with dual comp spectroscopy and with strong lasers is that you can also measure to thicker path lengths, and that you can do a lot of measurements also directly in aqueous solutions and not, you don't need to use always D2O. I think that's a huge advantage in when you're measuring transmission, generally spoken. So there is another question. What is the temperature during the measurement described in the webinar?
It was room temperature, so we were about 25 degrees. But the stop flow could be controlled. I mean, in this configuration from 0 to 70 degrees. Okay, that would be just the next question actually. That you can also, if you can heat that up and make, for example, denaturation studies, stress tests at higher temperatures. So you can go. You mentioned you can go up to 70 degrees, right? Yes, in this configuration, yes. Then there's another question actually about the dead time, or that is actually also something where probably a lot of people are interested. You mentioned the dead time limitation currently is 5 milliseconds. Yes,
Is there a possibility to go to increase that in the near future, that you can go even to the microsecond time resolution? Because now you have also the possibility to do so, which was probably not. So mid-IR spectrometers were not able to monitor microsecond time resolutions.
In this setup, actually the limitations is the calcium fluoride windows. Because they cannot take very high flow rate, they are sensitive to pressure, so we cannot use the full speed of the stop flow. That's why the dead time we have in this coupling is 5 milliseconds, but we only use the maximum flow rate we use is about 4 milliliter per second. When we use the stop flow in other applications like fluorescence, it is possible to push at 20 milliliter per second, so it's possible to decrease dead time down to 200 microseconds. So here the limitation is really the infrared window.
The infrared window,
yeah.
Okay. Yeah. Then another thing which would probably also highlight how easy it is to put that together. Can you probably highlight a little bit how fast we got those really nice results, even in intermediate, as we have seen in those few milliseconds?
Yeah, well, I think maybe to be honest, it took more time to prepare the samples than to do the experiment itself. So it was very straightforward because you just install the software and connect the accessory. You could slide it directly inside the sample compartment. So there is no special adjustment to do. And I mean, once the laser was already warm up, so everything was ready. So it was just a question to put the sample in and to run the experiment. So it was quite straightforward. Yeah.
Yeah, I think you talked a little bit about the triggering. I mean, we did in early times, Rafa and me, some manual triggering. We did that with a TTL trigger, right?
It's a 5 volts TTL. So yeah. We just the signal goes down from 5 to 0, and so we just connect through a small BNC to your electronics. This was working very well.
Okay. Then there's another question actually: which mixing ratio can be used?
Yes, we have an independent. Yeah, sure. So you could do mixing ratios on the full range, so from 1 to 1. So here in this configuration with this calcium fluoride small cell, probably the highest mixing ratio you could do is 1 to 50.
1 to 50, yeah.
Yeah, and it's pretty. I mean, you could do all 1 to 2, 1 to 3, 1 to 7, whatever you want. It's just control from software.
Okay. I see just another question is coming in here from what was the laser focal diameter at the sample position in the experiment? I think that was 3 millimeter. Yeah. I mean, when we were focusing in transmission, there was the focus was around 3 millimeter. And we did a lot of tests actually also in the webinar, which we did in March, which I recommend to watch probably as well with Carsten Kötting. We did there some measurements in transmission. And the big advantage is also that you use much less material than with other solutions. So the focus was around 3 millimeter. Okay, at this time, I don't, there's just another question coming in about the pre-triggering. How does that work? Okay, it's very difficult actually how this is set up. We use that actually also for combustion experiments, and we need that also to have first the background. It's very similar to an FDR spectrometer. I can't describe that directly in detail, but that's you have actually the recording before the measurement, before we really start the triggering as well. Yeah. And this is necessary because otherwise you cannot just do such high speed measurements.
Yeah, with the stop flow. So with the stop flow, you have two ways to control the pre-trigger. So if you do not put pre-trigger, so you just start acquisition at the time you stop the motor. Yeah. But because we have a full control of motor, we could send this pre-trigger before the stop. So normally we assume that when we do a stop flow experiment, we push enough solutions to reach a stationary state. So it means that just before we stop the flow, so during the pre-trigger, it's just like we have a starting solution inside the cell. So we record the background. Record the background on this pre-trigger. And then when we do the measurement, we just subtract automatically, I would say, the measured signal minus the background. That's why on the trace, I showed earlier, it was a change of absorbance on the y-axis. Yeah, delta absorbance was a change of absorbance.
Very nice, actually. And as I mentioned just before, now you're even available, or you can have actually the option just to go here to up to 268 milliseconds with such a high time resolution. I think that's really outstanding. So I see there are no further questions. I want to conclude that webinar and just remind you that we will put everything as webinar on demand, which will be uploaded by tomorrow around lunchtime. And there will be another webinar specifically for the people at Asia Pacific, and of course people also Europe area, which they can watch again, or if they had not the possibility to watch it today. And then as Cédric already mentioned, there's a lot of material on the BioLogic website. You will see probably also the recording of the learning center.
We have a learning center with a range of video or application notes. Yeah.
Exactly, where this will be probably recorded and is available for download later on. Then at the end, I just want to say merci beaucoup pour votre attention. Merci Cédric.
Thank you very much for all of you for attending this meeting. And if you want to know more, just do not hesitate to contact us.
Yes. Merci à tous. All the best.
Merci, au revoir. Thank you.
Merci.
Bye.